Good morning, everyone, and welcome to the fourth session of the Metabuilding webinar series. My name is Tommaso Francese, and I'll be your host today on behalf of R2R Solutions. Thank you for all joining us. Today's session is dedicated to the O3BET Façade Test Bench, and we'll explore what the O3BET actually is, what it can achieve, and how it is designed, actually. For those less familiar, this work sits within the Metabuilding ecosystem, which brings together research organizations and industry across Europe to accelerate innovation in the construction and building environment sector. The O3BET Facade Test Bench is one of the concrete outcomes of this project, collaborative project, and today we get a look under the hood. So to walk us through it, I'm delighted to introduce the four speakers. We have Antoine Dugué, that is the R&D manager at Nobatek and technical leader of the Metabuilding Labs project. Carmine Pasquale, responsible for European research at Stress-Cal in Napoli, and a board member of the Metabuilding Association. Cristina Parrado, researcher in the Digital System Division at Cartif, with a strong background in the construction innovation project. And Sylvain Kudiki, group leader for sustainable and urban and built environment at the Luxembourg Institute for Science and Technology, LIST. So I give the floor to Antoine, but before starting, just a quick note on the format before beginning. Please feel free to drop any question, in the chat at any point. We will address them during the presentation. Thanks a lot.
Okay, good morning, everyone. So I'll share my screen. Okay, now you can see normally my screen, and I'll start this presentation, which is dedicated to this O3BET. I'll explain later what it is, and the idea is to explain how it started, what was the purpose of it, and how we designed it. And then I will pass the micro to Cristina Parrado, who will present the first case of the O3BET. So this is the way we are going to present those presentation. So I will start with a very, let's say, weather-like approach. I'm not the weatherman, but the recent climate, the recent weather, obviously all struck us in Europe with high temperatures and so on. So this is just a fact. And what I want to stress with that is how in buildings and out of buildings, it affects all of us, Obviously on the health aspects, but also related to the life around us and so on. So the IPCC, in its different reports, actually highlighted the different, let's say, adaptation options to climate impacts at the scale of cities or buildings, And so what you can see there is how to potentially reduce thermal, how to improve thermal comfort in different situations, And the so-called adaptation options that you can see in the middle, amongst those, there is the sheeting, or there are green roofs, green walls, and those are the very solutions that we are going to consider for this webinar. What you can see there is that shading solution, green roof are assessed in terms of effectiveness, in terms of feasibility, and so on. So we could discuss about how to interpret the size of those paste, blue paste, and so on. But the idea is to say that those are solutions that can allow us to mitigate not only the impact of climate change, but also obviously to increase comfort in buildings. And from that, what I can present is how in summer, in the case of an office building, what's on the left, what you see is how the heat gains, so the cause of potential thermal discomfort or increased energy consumption in case there is a cooling system, what are they due? What are the causes? And mainly it's due to internal gains, obviously to solar gains and ventilation and envelope. What you can see there is although internal gains, well, there are ways to mitigate them and so on by adapting our usages. In the case of solar gains or even potentially ventilation and the envelope, obviously key there. So as a way to potentially avoid those increased heat gains for those, in the case of office buildings, we need to address those solar gains through the windows and the solar gains through the envelopes. Also, importantly, as a way to, let's say, cool a building as a passive solution, the most adapted one are obviously how to benefit from natural convection, natural ventilation during the night, limit solar gains through shading, and use inertia. So I just want to stress here how key the envelope of buildings is in order to limit thermal discomfort over the summer, which is something that we are all facing now. And so those envelope elements, you're going to have glazed areas, frames, so windows. This is obviously quite classic. Attached to those windows, you might find awning, you might find some more complex, let's say, in terms of design, shading solutions. You'll have also innovative solutions such as phase change materials integrated in materials or vacuum-based insulation, all those potential solutions. You'll have also shading solutions that are dynamic with different kind of controls. You'll have green facade. There are different types of those, either in front of glazing or directly installed on facade, on walls, on roofs, and also potentially BIPV. So those is just as a way to illustrate that there is a large variety of envelope elements that have a potential impact, obviously, on, as I presented in the previous slide, the solar gains, but also potentially even on ventilation and so on. So here, again, let's say that we have all the solutions that can be quite innovative, and the Metabuilding Labs project as its, let's say, core foundation was about how to bring those innovative envelope solutions to the markets. So what, let's say, barriers, challenges we were facing, okay? And one of those was, okay, but for those solutions, how can we evaluate their impact? How can we quantify it? How can we do it with accuracy? How can we guarantee it? It's more complex than, let's say, a basic static walls or windows. And another aspect was obviously, because we want to assist in their development, how do we consider regulations? And so we have to have obviously both, let's say, a physics-oriented analysis in order to assist potentially the manufacturers, industrials, designers, but also obviously comply with regulation or even push for an evaluation of regulations to facilitate, or let's say to the design and installation of such potential solutions. So I'm just going to have a quick overview of the Metabuilding Labs project and its outputs as we are closing this project. This is why we are having this webinar today. So it's first an ecosystem. So we have a series of partners. We have been working all together during 5 years. We have a platform. I will back on that. This is the metabuilding.com platform. And we have a single entry point, which is the association that is now the very core of the activity related to the Metabuilding Labs project. And we have the O3BET. As Tommaso just said, this is one of the key output of the project that I will be presented. We will all be presenting in the few minutes that we have all together. And so what we can say about the ecosystem is that, okay, we have few partners. Now the ecosystem is built around this association, okay? So, there is this metabuilding.com platform. I encourage you to go there and check what you can find there. Obviously, there were past webinars presenting the content of this presentation. That's another way also to learn about it. So it's, again, it was key in order to propose, let's say, a digital platform that allows all potential innovators, service providers, let's say, to meet, also how to put and share some key information about potential solutions, about capacity of laboratory testing, services, and so on. And so, as I said, what what is called a single entry point, meaning that all the services that can be delivered through this platform, through the laboratory, let's say, tests and so on, can go through the Metabuilding, which is an association. Metabuilding SPL is an association, okay? And so it's as an association, it has its members, and similarly, it's a way to encourage people to get more information about the potential motivation to join this association. So I'm back on the very topic that we are addressing today. So I'm going to use an example, one of the solutions that we had in this project, which is a green wall for renovation. So it starts with a simple idea, which is, okay, let's do a system that both allows to do some external thermal insulation, but also at the same time allows to have a climbing plant on it, so acting as a green wall. And so when discussing with Urban Canopy, was like the startup developing the system, there is an initial discussion. So they present a system, the system it's not finalized, it's still working on the design, but also wondering, having lots of questions and so on. Does it impact comfort, internal, external? Will it impact cooling loads? How can we integrate that into, let's say, business as usual energy models of buildings? Because there is no standards that could describe such solution. And so from this solution, we let's say draw market objectives, and okay, so we need to clarify the impact on cooling loads, the impact during summer comfort for potential residential office buildings, depending on the size of the building, depending on of its characteristic, and so on. And then we can go further. If it's for renovation, should we install it all over the building, or just select the buildings and the orientations that should be favored? And then, yeah, okay, can we also deliver a way to potentially model its impact when applying it into renovation? Okay, so that the next time your bank canopy or an architect, designer is considering using this solution, they can directly, easily have a good understanding of its behavior, but also on its potential impact on cooling loads, on thermal comfort, and so on. So the very simple idea there, and excuse me for the very simple graph, is that we are going to use, okay, which is not in this case the climbing plant, but this is a cell that you can see on the side of it, and so we have an internal volume, and we are going to install a solution on one open facade, which allows to have this installation on a 1-to-1 scale and real climate condition. The cell being highly insulated, most of the transfers are going through these openings where we are installing the tested elements. There are sensors. We are going back on these in a few minutes, but sensors that can be installed obviously in the cell or potentially even directly into the tested element. And then we are going to use some models and with the data that we are going to collect through the monitoring in order to identify the characteristics, the key performance indicators of the tested elements. And so if I go a bit further with that, okay, so the idea that was at the beginning, which is not especially new of this project, but the idea is to say, okay, for given envelope elements, we have to define the design, that you install it in such a test bench. We have to define obviously the protocol, and then we are going to carry out some tests, meaning that we are going to install it. We are going across few months, are going to collect data, and this data will be injected in a model. The model itself is to be designed, to be developed, depending on the characteristics of the tested elements. That we are doing to do some calibration in order to identify the open parameters, potentially a solar factor, potentially a conductivity, potentially a bit more than that. But so we are going to validate the model across this monitoring. And so in the end, the result is, let's say, the characterization of open parameters. Those parameters, which is quite key, can be dynamic. So we are going to consider more complex solutions which cannot be characterized under standardized method or cannot be standardized, let's say, in a lab. Okay. And so, very simply put, how we started. So what we did is that we assessed a large series of existing test benches. We had initial designs, and then we planned the monitoring. And so we worked, let's say, 1 year on requirements, 1 year on design, and then we get our version of these O3BET. The O3BET, I'm not even sure that I put it there. The BET is for Building Envelope Test Bench, and the O is for open source, open data, and open access. I will be back on explaining that in the final conclusion of this webinar. And so with those pictures of Valladolid, I will now pass the floor to Cristina to explain how from these initial concepts, Cartif was in charge of the design, and they built the first of those O3BETs in Valladolid in 2024.
Okay. Let me share my screen. Can you see it? Hello, can you see it?
No.
We cannot.
You can see it.
No.
I don't know why. We have full screen. It's not working, the button for sharing the presentation.
Maybe we can have plan B where Carmine can share the slides.
Yeah, it will be great. So,
Sorry for
sorry for that. Yeah, it's not working, the button. You can share my presentation. I will appreciate it.
We cannot hear you, Carmine.
Okay. Thank you, Carmen. Okay, thank you. Next one, please. Well, Yes, as Antoine said, we led the work package 4 in this project that was the responsible for the design, the construction, the commissioning and also the replicability of this facility that we have called O3BET. Next one, please. As Antoine said, initially the requirements that the installation had to meet were defined collaboratively, taking into account different aspects as the state of the art, the partner's background, and also the technologies that we could test. Among other dimensions, the facility covers approximately 80 square meters of surface area. We have two cells that the dimension of 5 by 3, with a south face in which we test the different facades, while the remaining 5 are located in what we have called this ward zone, that is a controlled environment zone. The material that we have used is wood, especially industrialized wood panels, and the effort that we have done with all the rest of the partners is at least the cells need to be the same material, the same dimension, but also the exterior of the envelope materials have been subject to some modification as climate or different rules of the different countries. Next one, Carmen. The design has been complemented with the BIM models, and especially we have had consideration of given the iteration of the systems to be tested as a BIM model, and we provide all the projects in an IFC standard for BIM. As Antoine said, we are following the requirements of open data, open source, and open access. Next one, please. But we have considered not only structural or construction-related design, also we have considered other elements. In this case, for example, the cable routing device, the airtightness system, the layout of the sensor, auxiliary components for the heating system, and the calibration wall to characterize the behavior of the cell. Next one, please. The process we have followed, as Antoine said, it lasts at least 1 year since we get the plot to construct the cell until we start the works. We have documented all this process. We have experienced different bottlenecks, and we have shared all with all the partners and try to avoid this for the next one. Next one, please. As I said, finally, in May in 2023, the civil work began. We start with a concrete perimeter wall, and we have also 8 reinforced concrete cubes that 4 for each of the cells. And these interior cubes, the wall and the slab that you can see here are essential because they support the prefabricated timber walls that we use to construct the O3BET. Next one. The coordination between the contractor and the work stream was crucial. While the civil work were getting underway, the 2D components for erecting the O3BET, the cells and the ward zone has been constructed off-site. So we reduce a lot the construction time. And we try to get a very good insulation with these panels. Next one. You can see the more photos of the structure and all of the rest in a wooden sleeper around all the perimeter wall. The work began with the assembly of the ward zone, then the cells, and finally the roof. And as you can see, this final one, we had the exterior of the cladding. The appearance looks concrete, but is wood also. The interior of the cells have the minimum size holes required route the cabling. And also we have a door in the north face that you can see in the picture. That was one of the challenges also, because we need to have a system that get a good airtightness, and also the U value had to be similar to the one of the wall of the cell. Next one, please. This is the final result. On the left, you can see the north wall, and in the right, you can see, well, on the bottom part, you will see some images of the south, where we put the facade that we are going to test. The first one is a system that we has developed just to close the cell when we are not testing. And in the last one, you will see the calibration wall that it's put it in the south wall. Next one. How we put this test, or how we connect it with our cell. We have developed what we have called the sample holder frame. This frame is the one that we, as I said, we mount all the components that we are going to test. It's a steel frame that is reinforced mainly at the bottom. We have inside an inner frame made of wood and insulation. And this frame, as you can see, can be removed and replaced. It's mounted in a steel support that it anchored to the wall. And this is fixed also to the cell with the screws that go all around the perimeter of the outside of the cell. So it's very easy easy to mount and dismount this part. And it give us a lot of versatility, because we can mount it in a warehouse or even in the cell. So we have different ways to install the different facade. Next one, please. As Antoine said about the sensors, we have like a fixed sensors in the outside that we use a weather station installed at 10 meters in the north wall in a pivoting tower. We have pyranometers to measure the direct and the diffuse radiation. We have sensor also positioned in front of the test wall. Everything is connected by this external electrical panel. So we introduce the cable to the cell. And next one. And also we would like to have a very homogeneity in the temperature gradient inside the cell. So we have included the PT100 temperature sensor that has been fit in this system that you see is like a white tube, because we try to prevent the effect of the radiation, and that also allowed us to have different points and weights to situate within the cell. We have also surface sensors mounted in all the walls. We have a black globe, a watt meter, a differential pressure sensor primarily used for the air tightness. And we have this labeling convention that we have established for the sensor just to facilitate both the identification and the replicability of that. And we have also small control panels, mainly for activating the heating system. Next one. One important element that we have included, at least in one of the cells, has been what we call the tiles. These are heat flow sensors that we have fit to all the walls to measure the heat loss through them and to have an accurate characterization of the behavior of our cell. Next one, please. We have the air tightness is important also in order to rule out the leaks and especially to simplify the models. these strips and bands that you see in the photos, they are normally used in passive house and systems. We have also heat sealants used in the cable page area. And we talk about this door. The inner door is an insulated wooden door with a perimeter is well sealed around all the entire closing edge. We had special handles also, and while the outdoor is an acoustic chamber style door that also ensure the airtightness of the cell. Next one. We decided, as I said, as a consortium and with the partners, that we had this heating system that consists of 3 resistors of 400 watts and 2 fans that they give the hot air from the inside of this box, in which are mounted into the cell. In addition, we have this airtightness system for the test. We do the airtightness test once before we test and after the test to see that if everything is working properly. And the monitoring system is mounted outside the cell. So just in the cell, we have the sensors and the element that we are going to test. Next one, please. All the sensors then are connected to this Keysight data logger. This is another of the requirements for the partners, that all of us, we are going to use the same elements, the same data logger. And also we have developed the software to acquire, collect, and transmit this data from the data logger to the local database, and also from this database to the bench server. We have used Python in accordance with the open system requirements, and everything has been Dockerized to facilitate the installation to the other partners. Next one, please. As I said, we do some initial tests, especially the airtightness test. We made some thermal tests, and we see that we have some leaks in the door. That's, as I said before, is an important point. So we need to remove this seal, and also we put some foam to prevent all the leaks, and we reach the value that we need for the initial to initiate the test. So next one, please. With this calibration wall, we start to use different powers. The best one is that we have reached in our O3BET is 400 watts. And we have do tests also with a different sequence of heatings. And as you can see, we have a very good homogeneity in the temperature, and also we have a lot of data to know the heat loss all around our cell. So we have characterized our cell properly. And now, next one, please. Yep. So once the cell has been tested and we see that the sensors has been verified that they are working correctly, the calibration wall has been removed, and we are now going to try, as Antoine do with urban canopy. We have another element. In this case, is a facade that they call hybrid wall by Ormipresa. It consists in a prefabricated element that had one of the concrete layers has been replaced with CLT. So this is why it's called hybrid system, concrete, insulation, and timber. I can show you a short video of the dismantling reassembly of this wall. And we need to This is the calibration wall that we had. As I said, this frame allowed us to do different configuration. We can put the facade in the warehouse or even there if we have the installation. We take off the calibration wall, and now we are going to install the omnipresent wall. They send the module, the full facade, and we organize with them how to install. All the final closing, we put some foam all around the perimeter of the wall, so we maintain the airtightness of the cell. Sorry, you don't see the lorry with the facade, but you will see in a minute. We put all the facade in the hole that we have for the test. And now we are going, as Antoine said, we don't have only the inner sensor or the sensor outside. We need to put also some sensor in the facade. We are going to use temperature sensor and heat flow sensors in the inner side, in the outside of this wall. And we would like to carry out some relevant tests if the weather allowed us, because we have had very high temperatures during this month. Next one, please. And as we mentioned from the beginning, the idea is to replicate this O3BET across Europe and work as a network to provide support to manufacturers in different countries and climate. Everything has been documented. We have several process working instruction in place to ensure that we work under the same condition. And now I will give the floor to Carmine, so he can tell us about the replication process of the O3BET. Thank you, Carmine, for your help.
Carmine, we cannot hear you. No. You are muted.
My microphone is on.
Okay, now you can hear you.
Okay, is it okay from your side? Do you hear me? Okay, so I don't know if you heard my introduction, but I'm Carmine Pasquale from Stress. We were in charge of building of expanding the O3BET concept to Italy, and we were involved in the process. So we have our O3BET Innovative Test Bench network all around Europe. Christina has showed you the images of each single O3BET. I wanted to show you the distribution all over Europe of our infrastructures And actually, the effort that was put in this activity within the project, because we have real places all over Europe in which we have gone through a whole process that we have been replicating. So what Cristina did in Spain, and thank you, Cristina, for all the effort, because she guided us with the design, we try to replicate everywhere in Europe. And this is the positioning and the where we found finally the place to install the O3BET in Italy, in Termoli, within the University of Molise premises. Actually, the effort started before, as Antoine showed. We've been analyzing the state of the art, and so we contributed with some examples from Italy. So we studied different test benches already in use in Italy, or we got some ideas and examples about how to build these infrastructures to have a movable structure, because one of the ideas was that we could also move them once we have used them in a position, then move them into another new position. Anyways, we started analyzing the first initial site for Italy was the University of Napoli campus in Napoli, being the University of Napoli, another one of the partners of STRESS. And so we did a deep analysis also about the shadows. As you can see, we had found the perfect spot next to the lab. We did all the surveys, 3D survey and 3D modeling for the solar shadowing. But then at the end, the most important thing was the urban feasibility. That did not allow us to perform this installation in Napoli. And so we moved to another partner of STRESS, the University of Molise, that allowed us and gave us a wonderful place in which we could install our O3BET in Termoli. This is the University of Molise in Termoli, and they had this lot next to the university in which they allowed us to build the O3BET. It's obviously a different climate compared to the previous ones, but you will see. Obviously, we started with the feasibility checks this time, so all the urban characteristics, and we ended up that we are in an area with scientific structures could be built, but nevertheless, we needed to have a urban plan modification at regional level to allow us this. This is a special construction at the end, so it needed a special permission. So we started, let's say, later than the expected, and we had obviously the design in Termoli was only to organize the O3BET in the lot, because we followed totally Cartiff's design for the object. So the cells are the same, identical. Also the external finishing is identical. We had to do some once we had the construction permit, we rushed. So I will show you some pictures of the construction if my computer supports me. This happened in 2024, between June and July. We did all this construction. So we started from scratch. We cleaned the area. We built the same. You see, this is exactly the same picture that Cristina showed you. We built the foundations, and then we started on site the construction just to speed up. Let's say the wood provider, that was a great company that we selected to an entire network in Italy, was very, very fast and transferred part of their off-site construction on site. So it seems like a joke, but they were very fast, and with the very severe conditions like the ones we are experiencing now, they built the entire O3BET within the month of July 2024. Then we have had, you see the details. This is exactly like Cristina showed you. The different materials, we obviously, we had not the same company, but the materials are from different companies with the same characteristics. At the end, the layers are exactly the same. They were installed in different steps, but exactly using the reference that Cristina provided. So we called it the Bible. and we followed the Bible till the end, and we are still applying all the great advice that came out from the first O3BET that was built. So you see here the different steps. The finishing in Italy is the same as in Spain. We had different materials for some components, but at the end, the performances are exactly the same. Obviously, also in our case, we had to take into account some local modifications, because we are exposed to very salty conditions and very exposed to very strong winds. So we had to modify the roof. And after we completed the original roof, we had to add another roof, a different roof with different components. And we had also had to seal the joints and the connection between the single panels, leaving only the lower section open, because otherwise too much rain came in, and also the salt was damaging the structure. Apart from this local adjustment, we have exactly the same components. So this is the sample holding frame that we adjusted on both cells, but we are only using one now. I see the comments from Maria Fonti. Hello, Maria. Yes, we knew about yours. And we have installed exactly like in Christina's example, we have exactly the same components built following the design provided by Cartif. So the doors, the external door of the cell is exactly the one that was built locally in Italy, following the design that Christina provided. We had the same conditions for the equipment too. And as you see, in the different steps of our installation, we used the prototype. Cartif also provided a 3D file for printing this element. They designed and prepared the 3D file. So we just printed the same exact element as Christina designed. We used the same configuration. There is small differences between the single O3BETs are related to the north wall, because the door is not exactly aligned in every single O3BET, but the cells are all the same, like the data loggers and the other components. I hope I gave you a very fast but useful example on how we did replicate. And this is the situation. Actually, it's not the real situation, because now we have the calibration wall that is being mounted today together with other sensors. But this is our O3BET, Italian O3BET within the Metabuilding Labs network built by Stress at the University of Molise premises. And this is all from my side. Thank you. Maybe Sylvain can now pass to the next section.
Yes, certainly. Thank you, Carmine, for the handover. Can you hear me well? Yeah.
Yes.
So thank you. Let me just switch my screen. Okay, so we will continue the set of presentations regarding this facade test bench, the O3BET, and how we did it in Metabuilding Labs. By reviewing, let's say, the additional digital tools that empower the operations of those infrastructures. I'm saying to continue elaborating on the digital tools because Christina already quite well elaborated on how the monitoring has been developed, especially in Valladolid. Okay, next slide. Yeah, so I'm Sylvain Kubicki from the list, and I will elaborate on this, let's say, angle, digital tools and digital twinning for the O3BET, for this kind of testing infrastructure. So let's dive into the topic. I think what is the point of developing digital tools? So today, the testing procedures, of course, rely on tools, measurement devices, but the whole processes using such facilities is highly or largely manual. Data collection tools are fragmented, so we know that there are sensors, they provide their own data feeds, data sets, data loggers, but also spreadsheets and specific or very specialized analysis software. And the problem the stakeholders are facing is that those tools are not talking to each other. It's not coherent. And who are the users we are dealing with here? We are dealing with the technology providers. Let's call them the clients, right, of the test beds, of the facade test bench. The clients, manufacturers maybe, that develop a new component and they need to test it. They need to have some form of feedback, right? Not waiting for weeks or months to get their report and analysis done. They need, if possible, some real-time visibility of what's happening in the test. And when a campaign is over, between campaigns, the operators, they repeat the same time-consuming configuration tasks. And this is what, with the digital tools, we were looking to improve, let's say, for the benefits of all these stakeholders. My presentation will be sometimes a bit technical, and I'm sorry for that. But I think it's important for us also to try to translate the trends that we are looking at the moment in the digitalization of the built environment into the specific applications that we can find in the O3BET. So the framework that we have developed is based on 3 layers. At the base, and maybe I can add the image, it's really to leverage on the digital twin, let's say, paradigm. So at the base, there is the physical part of the twin, or the physical twin, which is the building itself. So you have seen the facade elements that are being under test, the sensing infrastructure itself. And in the middle, the digital twins will develop the virtual models, including BIM model that Christina also showed or mentioned, simulation ontologies that connect those data together. So mirroring the physical assets. And on the top are the services that we want to develop and to offer, service layer. So that's the, let's call it operational intelligence that the operators and clients can actually use or interact with. So these 3 layers need to be connected, and we use quite classical approach of APIs that connect those layers. And I think I have this, let's say, also image that we conceptualized in the last years, which really aims to leverage on the digital twin paradigm, going from the pure data collection, which of course could be static, but also sense data that we can monitor, towards more, let's call it intelligence or maturity level, so that we can more and more optimize, automate, and indeed even maybe at some point actuate for the operation of the O3BET. So that's, let's say, the framework, the concept. But then very early in the project, and when we discussed with the partners, all the technical experts that we gathered in Metabuilding Labs, really we came to the point, okay, let's have some digital infrastructures, of course, that's needed, but what can actually operators and clients expect from such a digital tool set? And we came with, let's say, 4 main areas where we believe we can bring value with the digital layer. Data integration first, in order to capture and keep a full semantic record of every testing campaign. So who is testing what? Which sensors are being used for the specific or need or requirement? Which are the conditions, but also ensure traceability and future benchmarking. Second, visualization, that's obvious, but still maybe also a side benefit sometimes. Giving operators as well as clients a 3D visualization of what's happening, data outliers, airtightness within the facility, using the real-time sensor dashboards that are quite common in digital twins. And then third, the fault detection, where we used and formulated rules-based engine to detect the anomalies and alert eventually the operators in near real time. Finally, fourth, actuation is what we look at the end. Did not fully achieved, but formulated, let's say, within the project. So automated emergency protocols to make sure the tests are not, let's say, made invalid for some reasons and protect the integrity as much as possible, not waiting for human intervention. And how was this implemented? So actually, we had two input platforms that I will mention, but in a nutshell, we developed or deployed the digital services through modular and layered systems that connect the physical part that you see at the bottom of the figure here on the right to the digital services and formulate the end-user services at the end. And in Metabuilding Labs, we could rely on two specifically set data platform or platforms. The first one was mentioned before, BEM server, which really targets the O3BET operators and the managers, making sure the tests can run, the data can be recorded. And Build Semantics, which is a technology platform we developed at the list, which was more targeting, in that case, technology providers as the clients of those tools, trying to offer them the services I was just mentioning before. So there is an interesting step. There was an interesting step in our development while Cartif and Stress and the other partners were developing their facilities, and which was a lot of infrastructure works, as you have seen, even administrative. So in parallel, we deployed this 3D printed scale mockup to validate the full pipeline, also using the BIM model, providing also some basic sensor data. And this is what we achieved, some pictures of the interface. And the next step is really the deployment on the O3BET facilities. Maybe to conclude and highlight the key takeaways. First of all, so I showed how we define the conceptual and technical digital twin infrastructure, specifically for the testing of facade components, including using open standards. And I wanted to stress that for interoperability, we use the well-known ontologies that are mentioned here, IFC, SSN, SAREF. And we integrate semantic data graphs with RDF, all reasoning capabilities. And this is really what we look forward to automate as much as possible the reasoning and go beyond simple rule-based alerts. And third, and probably most importantly, also within the scope of our webinar today, the digital tools aim to empower all the actors, as you understood, the operators that gain real-time feedback, fault detection, monitoring of the facility and the ongoing tests, and the clients that gain direct and transparent access to the data on their component. And with this, I thank you for your attention.
I will, let's say, take back the presentation, trying to share some more elements. So we had the concept presented initially. Christina and Carmine showed two examples of O3BET, and Sylvain showed how now we are going to, or we have developed digital tools in order to better exploit it. So the tools that Sylvain showed are both about the management of the infrastructure, the monitoring, the data to collect, in order to alleviate the effort in order to use it, but also tools that allow the accurate services, meaning the calibration, the characterization, and finally with this digital twin, it allows rather a service for the client to be able to visualize and exploit himself the model. What I want to go back to is the example of the urban canopy and how we, let's say, close the loop from the initial request to delivery of results. So what I showed initially is how we go from a design protocol to the results. Okay, so this is the physical part, what we do on the O3BET. But what I will try to illustrate in the 5-10 minutes to come is how we have these virtual content parts, and that allows us to call it a semi-virtual characterization. So what we do is, through the physical part, we have a calibration of a model on a given O3BET, meaning on the specific tests. Okay, we have validated for each installation an O3BET in Cardiff during April to July 2026, for example. But the validity of the model stands. And so we can use then the model of the representation of a wall to be integrated in a more, let's say, global energy model. In our case, we use Energy Plus, and we are going to define buildings, archetypes of buildings. And by running the models at the scale of archetypes, but with integration of the detailed model of the element that we have tested and validated, we are going to be able to run thousands of simulation and exploit it in order to, for example, not only identify the model at the element scale, but its potential impact once installed on a building. So that's why we call the semi-virtual characterization. And so if we're back to this green wall for which we had those initial questions that I raised earlier, will it impact the cooling loads on the building? So what we did is, okay, we had initial discussion, we did the test. So we had installed, let's say, in this case, kind of basic, but it was a climbing plant as a green wall in front of an opaque wall, a series of pictures that illustrate more or less what we did. And then we get to the third point, the measured data. So we installed sensors initially that we had sensors in between the insulation and the concrete blocks, heat flux sensors, thermal sensors, and so on. What we did also in order to characterize the development of the vegetation is to take pictures out of those plants across almost a full year. And then by actually turning those pictures into binary images, we can actually identify some kind of coverage value, okay, which is something that characterizes the not only the area, but also the density of this vegetation. So this is an input for the model. And let's put it this way. So more analyses show that by considering, for example, the temperature either behind the cladding or behind the vegetation. So we had indeed this reduction of temperature allowed by this so-called green wall. But although it was as much as 15 degrees just behind it, it was reduced in the wall because it was highly insulated and with some inertia. So this is some direct conclusion that we drawn out from the exploitation of the measurements. Okay, and so once we have the test, the monitor data, we get to the virtual model. So we start with a simple, let's put it this way, RC model, for which we have already a quite good agreement between what is measured and what is calculated, but we can complexify it by adding, let's put it this way, just more info, more input, but be aware that the more open parameters, the more complexities to identify those. And so we have this model with some parameters, and especially the ones which are related to the impact of the climbing plants. And so what we need is open parameters for which we do not have any clue about the values. It can be on the solar transmission, it can be on the convection behind the leaves. And so we do this calibration by exploiting the data. Again, I'll be quick, but we use sensitivity analysis in order to classify the parameters to identify, and then we do some training and some validation of the values that we have identified. We select different, let's say, calendar period in order to do the identification and then the validation. This is something that is done into what we call the Corai library, which is an open source library that you can easily find in GitHub. And yeah, and so we are back in this stuff so we have this model. We have a model which is nice, but what can we do with this model? I mean, it's nice for the thermal guy, an engineer and so on, but it's not really useful for the client who came with a question which was, will it impact the cooling loads? So what we do is through questionnaires, we identify the typical markets that they are looking at, which is multi-residential building in France, rather older ones. And so we have these models that is validated, that we integrate, and then we run these simulations. And the simulation applied to 3 different areas in France, either with buildings with, let's say, EPC value rating of DE or above, or lower one, meaning like more recent buildings. And just it's a first assessment of the potential reduction of energy, of cooling loads achieved by just installation of green facade on the green wall, on the facade. And what we can add is, okay, at the moment, so we are able to print it and deliver it as a report. But what we want to do in the coming months is to be able to integrate that into a more dynamic output as a dashboard for the client to be able to explore the data, and so that it is even both for pedagogy but also for market incentives. It would be great. And so with that, I'm sorry, I went a bit quicker there, but it was for me also a way to illustrate that the idea of the O3BET is not about just delivering very accurate measurements or a model, but it is indeed to provide insightful answers to the potential clients' initial requests. And so as a conclusion, well, we have a Metabuilding Labs project, which is about to finalize, but we have this single entry point, meaning the association, Metabuilding Association stands. It is alive and it's ready to welcome potentially more members. We have 6 O3BET, as I said, almost finished. We are carrying out some tests. What we want to do is to still work, obviously, together after the end of the project to share, obviously, the experience, to share the calibration that we do on the O3BET. So that's what we call this O3BET network. And yeah, and as a final word, I could say that our end goal, again, is not so much to publish papers and so on, but rather to test solutions and provide results to potentially innovative solutions, as I said at the very beginning, that might allow to lower solar gains, or let's say to increase summer comfort over the years to come. And with that, I thank you all for participating or checking this video afterward on YouTube. And again, have a good day and bye.
So thanks, Antoine. I don't know if there is any question before making a final conclusion remarks. So let's wait 20 seconds. Time to write in the chat. Thank you. Okay, so before wrapping up, I'd like to invite you. We were born to invite you for the next webinar. Okay, we are going to have our 5th session on July the 10th, titled Ecosystem Advocacy and Linkage to Policy and Public Funding. So if today we look at the technical side of Metabuilding ecosystem, basically next week we will zoom out on the bigger picture, how this ecosystem connects to European policy and public funding, and how advocacy can help turn innovation to real impact. We will be joined by another excellent panel, including Antoine Dugué, that is the General Director of Metabuilding, Luigi Perisic from Fede Costituzioni, Claudia Unziker-Keller from the Head of European Affairs at Nobatek, and also representative of the Startup project, and Carmine Pasquale, again, on stress. So it's a conversation that you won't to miss because it's very interesting. So please register, and I will drop the link for the registration just in the chat for you to keep in the calendar. And if no other questions are placed in the chat, so thanks everyone for joining us, and see you all next week. And thanks for the speakers.
Thank you, Tommaso.
Thank you, all of you.
Thank you. Have a good day.
Bye.